Combinatorics, Lecture 1, Sets and Set Operations. In this course, we will address the following topics: fundamental enumeration principles, permutations, combinations, the Dirichlet box principle, inclusion-exclusion, recursion, generating functions, and classical probability. The main question which we will try to address during all lectures of the course is how to count elements of a given finite set. So let us start with a general recap on basic set theory. So informally, a set is a collection of some elements. Here is the usual notation for sets via an example. The set which consists of the elements 1, 2, and 3 is denoted in the following way, so you write 1, 2, and 3 in this kind of brackets. There is one set for which there is a special notation, and that's a set which has no elements. This is called the empty set, and this is denoted by this symbol. The fact that some element A belongs to a set X is denoted in this way. So this is usually read A belongs to X, or A is an element of X. The fact that A does not belong to a set X is denoted in this way, so A is not an element in the set X. So we should treat both these formulas as logical expressions, and so they are expressions which can either be true or false, so they take values in the Boolean algebra. Definition: two sets are called equal if they consist of the same elements. So formally, a set X is equal to a set Y if and only if for each element A is an element of X, if and only if A is an element of Y. So for example, the set consisting of the elements 1, 2, and 3 is equal to the set which consists of the elements 1, 3, and 2. So in particular, this means that there is no intrinsic order on the elements of some set. And this also means that the empty set is unique up to equality. So here are some other examples of sets. So we have the set of all integers, which is usually denoted by this mathematical style capital Z. So it consists of all integers 0, 1, minus 1, 2, minus 2, and so on. So here is the set of all real numbers between 0 and 1. So this is denoted in this way. So this is a segment, real segment, with endpoints 0 and 1. It consists of all real numbers x, which are greater than or equal to 0, and at the same time less than or equal to 1. Or here is a set of all complex numbers of absolute value 1. So these are the usual ways how you denote sets. You list the elements, or you say we take some elements from some other set which satisfies some conditions, and so on. Next, let us talk about subsets. A set X is said to be a subset of a set Y if each element of X is at the same time an element of Y. The usual notation is as follows, so this is usually read X is a subset of Y. Sometimes one can use this notation, but I would normally use the first one. So in the language of logical expressions, X is a subset of Y if and only if for each element A is an element of X, implies that A is an element of Y. Here is an example. The set consisting of 1 and 3 is a subset of the set consisting of 1, 2, and 3, because 1 and 3 belong to 1, 2, 3. Example 2 is that the empty set is a subset of any other set. Example 3, any set is a subset of itself. So each set is a subset of itself. Let us note that two sets X and Y are equal if and only if X is a subset of Y, and at the same time Y is a subset of X. And this is this property which is usually used to prove that two sets are equal. Now we can define the notion of the Boolean of a set. Definition: the set of all subsets of a set X is called the Boolean of X and denoted B of X. For example, the Boolean of the set consisting of two elements 1 and 2 has four subsets: the empty set, the set with 1, the set with just 2, and the whole set 1 and 2. Example 2, the Boolean of the empty set consists just of the empty set. Let us note that the empty set has no elements, while the set consisting of the empty set has one element. So one has to distinguish these two. A piece of terminology: a set with one element is usually called a singleton, and by convention it's quite often useful to identify elements with the corresponding singleton sets, which consist only of one element. So in particular, the element X and the singleton set consisting of X are usually identified for simplicity. However, there is a catch. If this element is set in itself, one should distinguish the singleton set from the set represented by this element X. So one should distinguish the empty set and the set which consists of the empty set as one element. Next, let us briefly talk about the cardinality. The number of elements of a set X is called the cardinality of X and denoted in this way, as the absolute value of X. Note that this cardinality is a cardinal number, and alternative notation for cardinality is as follows, which is quite often used when the set is given using the bracket notation. So for example, the cardinality of the set having elements 1 and 2 is 2. The cardinality of the empty set is 0, and the cardinality of the set of all integers is the countable infinity, so the smallest possible infinite cardinal, aleph 0. A set X is called finite provided that its cardinality is finite, that is a non-negative integer. And in this course, we will mostly study finite sets. For example, the empty set or the set consisting of 1 and 2 are both finite sets, while the set of all integers is not finite. Now let us talk about different set operations, and we start with the union. Let X and Y be two sets. The union of X and Y, denoted in this way, so X cup Y, is defined as a set which consists of all elements of X and all elements of Y. For example, the union of the sets 1 and 2 and 2 and 3 is the set 1, 2, 3. Another example: X union with X is equal to X for any set X. Example 3, the union of X and the empty set is equal to X for any set X. Let us observe that if X is a subset of Y, then the union of X and Y is equal to Y. So for example, the union of the set of all integers and the set of all real numbers is the set of all real numbers. Let us observe that the union of X and Y is equal to the union of Y and X. So the union is a commutative binary operation on sets. And let us also observe that X is a subset of the union of X and Y for any X and for any Y. The next set operation which we will discuss is intersection. So let X and Y be two sets. The intersection of X and Y, which is usually denoted in this way, X cap Y, is defined as the set which consists of all common elements of X and Y. That is, all elements of X which are at the same time also elements of Y. For example, the intersection between the two sets, the first one 1 and 2, and the second one 2 and 3, is the singleton consisting of the element 2, because 2 is the only common element of these two sets. Example 2, the intersection between X and X is equal to X for any set X. And example 3, the intersection between x and the empty set is the empty set for any x. Let us observe that if x is a subset of y, then the intersection between x and y is equal to x. So for example, the intersection between the set of all integers and the set of all real numbers is equal to the set of all integers. Again, the intersection, just like the union, is a commutative operation, so the intersection between x and y is equal to the intersection between y and x. And we can also observe that the intersection between x and y is a subset of x, by definition. Of course, it's also a subset of y. Next, let us talk about the difference between sets. Let x and y be two sets. Definition: the difference x minus y of x and y is defined as a set of all elements of x which are not elements of y. So for example, the set 1, 2, if we subtract from this set the set 2, 3, we will get 1. So the common element is 2, we should throw it away, and the rest is 1. So for example, x minus x is equal to the empty set for any x, and x minus the empty set is equal to x for any x. Let us observe that if x is a subset of y, then x minus y is equal to the empty set. So for example, if we take all integers and throw from the set all real numbers, the outcome will be the empty set. Let us note that the intersection between x minus y and y minus x is the empty set. And of course, x minus y is a subset of x. The next set operation is the symmetric difference. Let x and y be two sets. Definition: the symmetric difference x delta y of x and y is defined as a set which consists of all elements of x that are not elements of y, together with all elements of y that are not elements of x. So put shortly, x delta y is the union of x minus y and y minus x. For example, the symmetric difference between 1, 2 and 2, 3 is 1, 3. Example 2, the symmetric difference between x and x is the empty set for any x. Example 3, the symmetric difference between x and the empty set is x for any x. So we observe that if x is a subset of y, then the symmetric difference between x and y is y minus x. Now the symmetric difference is commutative. The symmetric difference between x and y is equal to the symmetric difference between y and x. And finally, the symmetric difference between x and y is a subset of x union with y. Our final set operation is complement. The setup to define this operation is as follows. Assume that we have the universal set U, which we call the universe, and all sets that we consider are subsets of U. So now let X be a set, and as we just described, it should be a subset of U. Then the complement of X, denoted by X overlined, is defined as a set of all elements of U that do not belong to X. Or, if we put it shortly, X overlined is just U minus X. For example, if U is equal to the set of all integers, then the complement of the subset 1, 2 is the set of all integers 0, minus 1, minus 2, 3, minus 3, 4, minus 4, and so on. One important property is that taking the complement twice, we come back to the original set X for any X. And another property is that taking complement reverses the inclusion. If X is a subset of Y, then the complement of Y is a subset of the complement of X. Now let us briefly talk about Venn diagrams. For abstract computations with sets, using the above operations, it is often convenient to use the so-called Venn diagrams. In such a diagram, a set is depicted as the inner part of a closed curve on a plane. And usually this curve is a circle or something which is very close to a circle. For example, here is a Venn diagram which depicts the union of two sets. We have two circles, one representing a set X and another one representing a set Y. So the colored part of this picture consists of all points which are inside the circle of X or inside the circle of Y. So here is another example. It's a Venn diagram depicting the intersection of two sets. Again, we have a circle which represents the set X and the circle which represents the set Y, and what is colored here are the common points, the intersection of X and Y. And here is yet another example. So that's a Venn diagram depicting the symmetric difference. So that's X delta Y. Again, we have the circle for X and the circle for Y. We take the union, which is depicted by both circles, and then we take out the common part. And what remains is exactly the symmetric difference X delta Y. The union of X minus Y here and Y minus X here. So here is one example of how one can use Venn diagrams to prove relations between sets. So here is a Venn diagram proof of De Morgan's law, which says that the complement to the union of X and Y is equal to the intersection between the complement of X and the complement of Y. And here is the Venn diagram proof of it. Here on the left-hand side, we have the set X, the set Y, so we have the union, and what is colored is exactly the complement to this union. And here on the right-hand side, we have the same set X, the same set Y, and then we first color the complement to X, and then the complement to Y, and then the common part is the intersection, and so we see that what is not the common colored part is slightly lighter color, and now we can compare the common part here with what is colored on the left-hand side and see that they coincide. And this proves this law, which says that the complement of the union is equal to the intersection of the complements. Finally, let us discuss the notion of a Cartesian product. So let X and Y be two sets. Definition: the Cartesian product X times Y of X and Y is defined as a set consisting of all elements of the form A, B, where A is an element of X and B is an element of Y. And that we use these kind of brackets tells us that now we are concerned about the order of elements in this pair. For example, the Cartesian product of the set 1, 2 and the sets 3, 4 consists of the following pairs: 1, 3, 1, 4, 2, 3, and 2, 4. Let us remark that X Cartesian product with the empty set in any order outputs the empty set. And here is the standard notation. X to the power k is defined as the Cartesian product of X with itself k times. For example, we are all familiar with the real plane, which is denoted by r to the power 2. So that's the set of all pairs of real numbers, where we now identify the real plane with the coordinates of the points in this plane. We can use the notion of Cartesian product to define the notion of a function. So let X and Y be two sets. Definition: a function from X to Y, which is usually denoted by phi, goes from X to Y, is a subset of the Cartesian product of X and Y, which has the following property. For any element A in X, there is a unique element B in Y, such that the pair A, B belongs to this function phi. And this is usually written B is equal to phi of A. So if A is an element of X, then there is a unique B such that A, B belongs to phi, and we write it as B is equal to phi of A. For example, we have the usual real functions y is equal to x plus 1, or y is equal to x squared, or y is equal to sine of x, and they all are subsets of the real plane, r to the power 2. So we identify in this way a function with a graph of the function. Another example, for any non-empty set y and for any element b in y, we can consider the constant function cb from any set x to this y, which sends all elements in x to this b. Example 3, if x is equal to y, then we have the identity function on x, which is defined as follows. It sends each element a in x to the same element a, to the element a itself. And finally, let us define the notions of injective, surjective, and bijective functions. So let x and y be two sets, and let phi be a function from x to y. Definition. The function phi is called injective if for any elements a and c in x, which are different, we have that phi of a is different from phi of c. The function phi is called surjective if for any b in y, there is a in x such that phi of a is equal to b. And the function phi is called bijective if phi is both injective and surjective. For example, the identity function on a set x is bijective. Example 2. A constant function from x to y is injective if and only if x is a singleton, and it is bijective if and only if both x and y are singletons. Some additional problems and questions at the end. Problem question 1. Find all possible sets x and y such that x union with y is equal to 1, 2. Problem question 2. Explain why 1, 2 intersection with 2, 3 is equal to 2, but the intersection between two singletons, one consisting of the set 1, 2, and another one consisting of the set 2, 3, is the empty set. Problem question 3. Prove using Venn diagrams that the complement to the intersection of x and y is the union of the complement of x and the complement of y. Problem question 4. Write down all functions from 1, 2 to 3, 4 and determine which of these are injective, which are surjective, and which are bijective. Problem question 5. Write down all functions from 1, 2 to 3, 4, 5 and determine which of these are injective, which are surjective, and which are bijective. Thank you very much and see you next time.